These notes are on calorimetry. Hopefully you downloaded the fill in the blank notes so that you can follow along and see how to do these examples. So calorimetry, what is it? It's really a lab technique, and I know that we're applying this kind of to our reactor, but the idea is that if you have a system that is closed, meaning that no energy from outside can get into or out of your system, that any energy that's present has to still be there. It has to be transferred. So if our uranium rods have all this energy it's releasing, if it was in this closed system where none of that heat could get out at all, then 100% of the energy would be transferred into the water that we're trying to heat under pressure. Right? If all of a sudden it releases 1,000,000 joules of energy, then the water is going to absorb that 1,000,000 joules of energy, and by taking in that 1,000,000 joules of energy, it's going to make it get warmer if it doesn't go through a phase change, right? And it's not going through a phase change because we know it's under pressure. So calorimetry, right, a laboratory technique that determines the amount of heat transferred in a chemical or physical process. So if you were to do this in a lab setting, right, which typically, and you'll see that we will do this lab, that you can use the specific heat of a material to kind of identify it and see what it's made up of. And so that's what we're going to do, is we're going to do this lab, or you're going to watch a video of the lab, I guess, to see this kind of process. Right, so instrument used to minimize the heat lost to the surroundings, which usually has to do with some sort of, in a public high school setting, some sort of styrofoam container, styrofoam cups. And so it has a thermometer in it. So this would be the really cheap version, literally 2 styrofoam cups just to try to insulate it. I have a little better one, not a whole lot, but a little bit. And then you need a thermometer to see what the temperature of the water is inside. Okay, so how does it work? Right, you have water in this calorimeter, and you need to know how much, because remember, if we're using an equation that's Q equals mc delta T, right, we need to know how much water so that we know the mass of the water. We're going to use that thermometer to figure out the initial temperature of the water, remembering that the change in temperature is final minus initial, right? And then we know that it's water, so our heat capacity is 4.184. So water placed in the calorimeter, the initial temperature is taken along with the mass. A second substance is heated, and its initial temperature is recorded. So in this case, we're going to heat up, a piece of metal and record the mass of the metal and the temperature of it. So it says that both masses, the water and the substance, are recorded, and then the substance is placed in the water and the lid is quickly placed on. So in our case, it's going to be a metal that we place in the water. In the case of our kind of scenario for our whole unit, right, we're talking about the uranium rods are the substance, but they're constantly releasing heat. So it's kind of a little bit different of a scenario, but you kind of get the idea of it. So it could be a chemical, it could be a powdered chemical, it could be a warm liquid and a hot liquid that you mix together. It doesn't have to be a solid mixed in the water. It could be really anything that you put in that water. So 5, the experimenter, that's us, records the temperature change in the water until the temperature is constant for a number of readings. So we're going to be looking for the temperature of our water. If you think about it, if we have this container full of water, right, at a certain temperature, if we put something that's really hot in that water, well, what's going to happen to all the energy that all these particles have in this metal because it's really hot? We know that it has these chemical this kinetic energy, right? They're vibrating around. Well, all that energy, not all of it, but some of it is going to be transferred into the water. And so if it's transferred into the water, we know from our equation, right, that if this change in temperature is positive, if it gets warmer, that's because the energy was going into that substance. So in this case, our water is going to be endothermic. It's going to be taking in the energy. And our metal is going to be the exothermic part of that, where it's going to be releasing energy. So our water is going to get hotter. Our metal is going to get colder until it reaches a constant temperature. Right at this point, it's in equilibrium or thermal equilibrium, and so we will record that temperature. Okay, and if I'm going too fast, hopefully you're pausing to get it all down. So calculations, when two substances are added to each other and allowed to come to one temperature, it's in dynamic equilibrium, or you could call thermal equilibrium. The heat lost by one, which in this case, I've been talking about a metal, so the heat lost by the metal is going to be gained by the water. So we are going to have our piece of metal have a negative Q because it's releasing energy, right? It's exothermic, and that is going to be gained by our water. Well, if we lose 100 joules of energy, right, the metal does, then that means our water must gain the 100 joules of energy, because remember, we have this closed system, that all the energy in our system stays in our system. It doesn't leave and go to any of our surroundings. So energy is conserved. Okay, so, right, we talked about that. So what does that look like? So looking at this problem, man, there's a lot of numbers in there, right? 45 grams. Well, what do we measure in grams? Measure mass in grams. Joules per gram degrees Celsius. Well, that's a C. Degrees Celsius, that's a temperature, right? More joules per gram degrees Celsius, that's another C. Here's another degrees Celsius. Here's another temperature. Here's another temperature. So I haven't even read any words, and I already know that I've been given some masses, I've been given some heat capacities, I've been given some temperatures. So we just need to figure out what all of these go with, and obviously that has to do with reading it. What I'm going to do is I'm going to separate all these values into our two substances. Okay, you can see that we're going to be talking about copper, and we're going to be placing it in water. So I don't just want the heat capacities and initial temperatures, final temperatures, and mass. I need them for each thing, the copper and the water, and I've got to keep them straight. So a 0.45 gram piece of copper, so we know that's the mass of copper, and it gives us the heat capacity of copper at a temperature of 87 degrees. So that's our initial temperature, right? The copper starts at 87, is placed in a calorimeter. The calorimeter contains water with a heat capacity at a temperature of 23.0 degrees Celsius. So that's the initial temperature of the water. The solution came to equilibrium, right? This is that thermal equilibrium, so they're the same temperature. So this here, that's the final temperature of the water and the final temperature of the copper. They're both the same temperature. What was the mass of the water in the calorimeter? So this is what we're looking for, the mass of the water. So this is how I would suggest doing it. I would list your substances and then start listing what you know, right? We knew the mass, the heat capacity, the initial temperature, and the final temperature. And then water, there's our other substance. What do we know about water? We knew the heat capacity, we knew the initial temperature, right? Both final temperatures are the same, and we were looking for the mass of the water. Okay, so we are going to use the equation that we were using before, right? Q equals mc delta T. And we're going to figure out that out of all of this stuff, whatever they're asking about, right? They're asking something about water. You're going to go to the other substance and figure out how much energy was gained or lost. right? They ask about water, we're going to start with copper. If they asked about copper, we would start with water. You're going to be given enough information for one substance to solve for that heat. Okay, so here we go, and this will go fast, right? We're going to plug in our givens from that previous page, making sure that this is final minus initial, and we're going to figure out that the copper lost energy. Well, if the copper lost 10.78 joules, where did it go? It went to the water. The water gained those 10.78 joules. So the water now is a positive 10.78, right? It's endothermic. It was taking in that energy. It was absorbing that energy. So now we do Q equals MC delta T again, but now it's just for water. Everything we're going to punch in there is water, right? We know that the water gained this energy that the copper lost. We know it's final minus initial with its heat capacity, so we can solve for the mass, right? 1.4 grams of water is how much water was in that calorimeter, right? The heat lost by one is gained by the other. And so our Q's were opposite signs. Let's do one more, right? A piece of titanium, so there's our one substance, has a mass of 20.8 grams. It's heated in boiling water to 99.5. Well, if our titanium is in water that's boiling, we're going to figure that this is the initial temperature of our titanium. It's dropped into a calorimeter. We know the mass of the water, the heat capacity of the water, and then our initial temperature of the water, 21.7. The final temperature in the calorimeter is 24.3. Remember, this final temperature is the temperature of both the titanium and the water because they're in equilibrium. What is the heat capacity of titanium? So we're looking for C for titanium. Again, listing out all those givens. Remember, they're asking about titanium, so I am going to start with water this time. So starting with water, I punch in my values, my mass, my heat capacity, my final minus initial temperature, and I find that my water gained 815.88 joules. Well, if it gained all that energy, where did it come from? Well, it came from the titanium. So the titanium lost, so we're going to say it's a negative 815.88 joules for titanium. Using that same equation, right, we're losing the energy over here. We've got the mass of titanium, the change in temperature of titanium. Do a little bit of algebra, right, which you don't have to show, but you do need to do to get the right answer, right? I'm subtracting these numbers, and then I'm multiplying that answer to 20.8. I'm now going to divide each side by the 1,564.16 and then negative 1,500. That gets me my heat capacity, and so now I know the heat capacity of titanium. That is it.